So, welcome to this next lecture. We have been talking about dynamic matrix control, and for the unconstrained problem what we saw was that my predictor is hence p step predictor is y hat predicted, the vector for a CISO system is equal to the dynamic matrix G times the set of control moves that are to be taken over the control horizon plus the vector of free response. Free response corresponds to no control action. If all the delta u's are 0, how would the output move? Okay. So, this was my n step predictor, and if I am trying to minimize over the unknown future control moves, E transpose E plus, where these are vectors, lambda times delta u transpose times delta u, which corresponds to close set point tracking plus lambda times control effort. Okay. If I am trying to minimize this, and just to understand this better, this E transpose E, actually E corresponds to, E is equal to y predicted minus the reference trajectory. Okay. So, what we have in essence or in effect is that we are trying to minimize, if you want to look at it in its full form, what we are trying to minimize is y transpose I being the time index. So, I goes from next sampling instant to p sampling instants ahead minus reference trajectory I whole square plus lambda times summation I is equal to 0 to m delta u I square. Okay. So, this is my objective function, and I am trying to figure out what should my delta u be such that this objective function is minimized. By the way, notice from the objective function that the more the lambda, the more penalty I am imposing on delta u's. That means, if lambda is increased, control moves are getting penalized. Okay. So, this is called the move suppression factor, move suppression factor. M is the control horizon, P is the prediction horizon, and I have my predictor up there. Okay. So, we saw that the unconstrained solution for this is the unconstrained solution is delta u star star indicating optimum is equal to G transpose G plus lambda I inverse times G transpose times okay. Yeah. So, this was the solution that we looked at last time. Of course, there are always constraints, and those constraints are two of the most common constraints in any loop would be that I want to minimize over delta u the vector E transpose E plus lambda times delta u transpose delta u. Okay. And subject to two of the most common constraints, delta u modulus, the maximum change in any of the elements has to be less than delta u max. For example, in one time instant you can only move the valve, let us say, by 2% or 5%. You cannot change the valve position in one time instant or in one sampling instant by more than 5%. You cannot expect the valve to go from 0% to 100%. Okay. So, there will be this constraint, and of course, there is always the constraint that the actual signal to the valve, which is U, should be between U max and U min, and U max would typically correspond to a fully open valve and U min would correspond to a fully closed valve. All right. So, for solving this problem, now this becomes a constrained quadratic optimization problem, and it is a constrained optimization, and there are what are known as quadratic programs that are pretty efficient at solving these types of problems, where the objective function is quadratic in nature and the constraints have certain properties. Okay, and this is referred to as QDMC, quadratic dynamic matrix control, and one of the most that I know of that I use quite often is quad prog in MATLAB. This command or this function is this subroutine is does solve quadratic programming problems. Okay. So, quad prog in MATLAB is typically invoked. There is a lot of theory that goes into, and I do not think we will go into it here. The point to be noted is, what I am trying to do is figure out the best control moves which are here, so that what should my delta U be, my future set of control moves be, so that my objective function is minimized, and my objective function is trying to minimize the deviation from the reference trajectory and the control effort. Okay. So, you want as close you want y to go as close as to the reference trajectory without too much control effort, that is what I am trying to do through this minimization problem, and there are standard algorithms that do that for you. Okay. Now, I have calculated, after I do whether it is a quadratic program or whether it is an unconstrained DMC, I have calculated my delta U, and delta U is actually the small step that I should take right now, the small step that I should take in the next time instant, and so on till delta U m. I am at the current time instant, this one gets implemented, okay. So, this control move gets implemented, and then I wait for the next sampling instant. At the next sampling instant, I get my new measurement, and then I repeat this whole process all over again. Okay. So, I am here, I do my optimization, calculate what the future set of moves should be. Of those future set, the current one gets implemented, and then at the next time instant when I get here, I repeat the whole process all over again. This is how DMC or most MPC techniques, the techniques may differ in how in the kind of predictor that they have, but essentially they are common in the sense that you got a quadratic objective and you are trying to minimize that objective by figuring out what you should do to the control input over the control horizon, the future control horizon. Okay. So, this is how DMC in particular is done or is implemented. What else? Okay. Some of the things that we have missed, which are worth pointing out right now. We have looked at right now CISO DMC. I will generalize it to MIMO systems in a little bit. Tuning parameters, how do you tune? Just like you got a PI controller or a PID controller where you have Kc, tau I and tau D. Tuning, what are the parameters in your hands that you can adjust to get the kind of control performance that you want? Okay. To do that, or you can think, what should be my control horizon? M. What should be my prediction horizon? P. I can also think of that move suppression factor lambda. This move suppression factor, actually, if you try and minimize E transpose E with lambda equal to 0, what you will find is you get very aggressive delta U's. Delta U's are very aggressive, large changes in delta U's, and when you start making large changes in your control input, that essentially drives the feedback loop or the control system towards instability. So, to stabilize your feedback system, that is why we added this lambda times delta U transpose, delta U term. This lambda is a tuning parameter and it is called move suppression factor, like I told you just a little while ago. It is a tuning parameter, and this is something that your control, what should I say, control system designer adjusts to get the kind of closed loop performance that he wants. If you choose too small a value for the control horizon, then the controller can only make so many control moves to ensure set point tracking or close set point tracking or close reference trajectory tracking. Okay. That being the case, if this is small, your controller becomes aggressive. It will try and make all the moves that are necessary, so that in the future the error in the predicted output is as small as possible. So, small m's will lead to an aggressive controller, large m's would lead to a sluggish controller. Similarly, for the prediction horizon, same thing. Okay. Note that P would typically be much larger than M. How much should you predict over? Well, at least one time constant. If the response takes 30 minutes to line out, step response, you should be making a prediction for at least 10-15 minutes. Okay. And M would typically be, say, 1/2 or 1/3 or maybe even 1/5 of P. Okay. The problem, well, there is another tuning parameter that I should talk about. See, we did not talk about the reference trajectory yet. You see, when I wrote error, I defined error as y predicted minus the reference trajectory. How do you get the reference trajectory? This is something that I will discuss right now. Let us say I am here. This is where my y is, and my set point is here, and of course, this is time axis. So, y current is here, y measured, y set point is here, that is where I want to be. Well, then the reference trajectory is typically defined as an exponential rise to the set point from wherever you are. Okay. This exponential rise can be fast, that is a fast exponential, or it can be sluggish. Okay. And one of the ways of doing it is to say that R I is equal to R I minus 1 times alpha plus 1 minus alpha times, I would say it should be, well, y set point I, which would typically be constant, y set point I. Okay, and we will say that I goes from I is equal to 1 to large, and at I equal to 0, R I is equal to y, R 0 is equal to y measured. Okay. Notice and alpha is typically between 1 and 0. So, if I say alpha is equal to 1, if I say alpha is equal to 0, alpha equal to 0, what I have is R 1 will be equal to 0 times y 0 plus 1 times yi set point. That means, at the next time instant, if I am here, at the next sampling time instant, my reference trajectory would be, my reference point would be this. Okay. So, that is like a step increase to the set point. Okay. That is my reference trajectory. As I keep increasing alpha from 0 to 1, I get more and more damping. So, as alpha increases, I get slower and slower rise to the set point. Okay. So, you can imagine that again this alpha is a parameter in the hands of the control system designer. If you choose small alpha, I want a fast rise to the set point, what that would do is make my control system aggressive. Okay. So, and the larger alpha I use, the more sluggish the control system becomes, alright. So, alpha, lambda, m and p are the tuning parameters that are in the hands of a control system designer to tune your model predictive controller to get the kind of response that is desired, to get the kind of control performance that is desired, tuning parameters. What you would have is typically designers would choose reasonable values for these, fix them to reasonable values, also take alpha to be a reasonable value, a reasonable exponential rise, that is alpha will have to be chosen appropriately for that, and then adjust this adjust the lambda to get whatever it is, whatever is the type of closed loop control performance that you want. Okay. The problem, I would not call it a problem, is just even though model predictive controllers have existed for so many years, how do you choose reasonable values of alpha, lambda, m and p? You see, if you have a PI controller, things are very simple: get the ultimate gain, get the ultimate period, and then you got your Ziegler-Nichols tuning table or a Tyrus-Lieben tuning table, etc., 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 and that tuning table you can implement, and that tells you what are your reasonable values for Kc, tau I and tau d. So, there are standard tuning methods for PID controllers. Unfortunately or fortunately, model predictive controllers, there are yet not systematic standard procedures that can be applied to get alpha, lambda, m and p. Okay. It is more hit and trial. You keep on adjusting lambda until you get the kind of control performance that you want. Okay. So, tuning is essentially hit and trial, and that is one of the major disadvantages, of essentially all MPC techniques, all model based control techniques. Okay. And therefore, because the tuning is not trivial, you do not have a standard procedure, just blindly apply it and there you are. It requires effort, and engineers being lazy engineers by definition, somebody remarked, engineers by definition are lazy people. There has to be significant justification to justify that, okay, if I apply model predictive control, sure it will take me effort to build and tune that controller, but that effort is worth it because it brings about such and such a significant improvement in control performance, and that significant improvement in control performance is actually translating to, for example, extra profit. And when I say extra profit, that is not just a few dollars, substantially extra profit. Okay. So, this trade off is always there. Model predictive control takes effort, takes time to design. What is the benefit that it brings, and when is that benefit good enough to justify putting in that much effort? Okay. That trade off is always there, and one needs to be aware of it. Hopefully, as we go through this course, you will get to see where MPC makes sense and where a PI or a PID controller would do just fine. Okay. But that is for later. one of the advantages of MPC is that it can be readily extended to MIMO systems, multiple input, multiple output. For the time being, let us just consider a square system. If you take a square system, then what you have is you have got output 1, output 2, and let us just say output n. These are outputs that need to be controlled, and in order to control these outputs, you got u1, u2 and un, these control inputs. Okay. Now, if I want to predict, for the sake of convenience, let us just assume that we are predicting y1 to yn over the next p time instants, and u1 to un are going to be moved, or the control horizon for each one of them is again m. Just for the sake of convenience, it is not necessary. Okay. So, prediction horizon is p for all the outputs, control horizon is m for all the inputs. Okay. Just for the sake of convenience, let us say we are doing it like this. Then, if I want to predict y1, meaning y1 predicted at time 1 from now, y1 predicted at time 2 instants from now, and so on, y1 at time p from now, hat indicating prediction. If I want to do this, what I will have is, I will have the dynamic matrix G11 times delta U1, the effect on output 1 of input 1. Okay, so, there will be a dynamic matrix corresponding to the 1-1 pairing, that is G11 plus. So, you see if I change output 2 or input 2, that also affects y1, that effect comes through the dynamic matrix number 2, which is G effect on 1 of input 2 times delta U 2 plus effect on 1 of input n times delta U n. And by the way, what is G11? G11 is equal to, I give a small unit step change to delta U1 to input 1. So, this is unit, and in response to this I record what happens to output 1. So, this is U1 and this is output 1, and this change in this record of output, the transient response of output 1, this gives me coefficients G for, and these step coefficients are what go, we had discussed this earlier. Right. What happens, what is G12? Well, I give a small step to input 2, record what happens to output 1. Those coefficients go in G21, right, and so on so forth. What is delta U1? Delta U1, the vector is and so on, change in input 1 m instants from now, right. Similarly, what is delta U2? Well, delta U2 will be, just have to rub this off, delta U2 change in input 2 right now, change in input 2 1 instant from now, and so on so forth, change in input 2 m instants from now, okay, and so on and so forth. You can define delta u1, delta u2, delta un. Okay. Prediction of how output 1 would respond over the prediction horizon, which is this guy, to changes in u1, u2 and un, to changes in the inputs. Okay. So, what I have, I mean, if I write this in matrix form and I simplify this, what I have then is y1 predicted over my prediction horizon comes from here. Similarly, I will have y2 predicted over the prediction horizon would be dynamic matrix G on 2 of 1 delta u1 plus G on 2. By the way, these are all matrices, just to clarify that, on 2 of input 2 delta u2 plus G on 2 of input n delta u n, and so on so forth. I can do this for all the outputs, and what I get is on n of 1 delta u1 plus on n of 2 delta u2 plus on n of input n delta u n. Okay. And you can see, if I put all of this in matrix form, what I then get is y1 predicted, y2 predicted, and so on, yn predicted is equal to G11, G12, G1n, G21, G22, G2n. By the way, I made a mistake. That mistake is a minor one, but okay, this is the prediction because of control action, plus of course there will be the free response. I forgot the free response. The free response of output 1 plus the free response of output 2 plus the free response of output n. If I do nothing, how would the outputs 1, 2 and n change over time? Okay. So, there is also the free response component. Okay. So, I think I forgot that. Okay. Blah 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 G n1, G n2, G n times delta u1, delta u2, delta un plus f1 free response in 2, free response in . For this multivariable system, I again find, if I call this vector y hat is equal to the G, this whole big matrix is the multivariable dynamic matrix now, big G times delta u, where this is what is being called delta u, plus where this is what is being called f. If I call this f, if I call this delta u, and if I call this G the matrix, and if I call this Y the prediction. Notice I had a very similar equation for a CISO system. So, what we are saying now is whether it is a CISO system or a MIMO system, multiple input multiple output, my predictor is the same, is of the same form, and therefore, if I am looking at unconstrained optimization, minimize over delta u E transpose E, where I have got reference trajectories for output 1, output 2, output n, plus lambda times what? Man, I do not know, lambda times delta u transpose. By the way, here I can have, well, do not worry about it. I could have different lambdas for different control inputs. There is also the issue of scaling the y's so that they get relatively the same weightage. But if you do not worry about those scaling equations, the point is that the form of the equation is the same, and therefore, the minimum solution will also correspond to the same form. Unconstrained solution would be delta u star will be the same thing, G transpose G plus lambda I inverse times G transpose times R minus F. Okay. Okay. So, the formalism remains the same whether it is a single input single output system or a multivariable system. I did all this for a square system where you had n inputs and n outputs. This matrix methods can also handle non-square systems. The formalism would still remain the same, and I would not like to go on it because then that becomes a course on process control, and it is really not essential. Okay. So, the point is that advantages of MPC, DMC being one of them. It is truly a multivariable technique. Notice that when I am inverting this matrix, and since this matrix has got all the components in it, meaning this matrix has got all the components in it, G11, G12, G21, G22, all the so this matrix takes care of effect of U1 on Y1, U2 on Y1, U2 on Y2, and so on and so forth. And I am inverting this matrix. The control moves that I get, what I mean to say is the delta u that I will get. So, delta u1, what I do to control input 1, depends not only what E1 is, error in variable 1, but it also depends on other error in 2, error in n, and so on and so forth. So, this what should I say, the calculation of the optimal control moves, which comes through either metric inversion or through quadratic programs, it is naturally multivariable. That means, the change in input 1 depends not only the error in input 1, but also error in input 2, the change in input 1 depends not only on the error in output 1, but also on the error in output 2, output 3, output n. So, how I move input 1 depends on all the errors. How I change output 2, input 2 depends on again all the errors. So, in that sense, the multivariable formulation of DMC or MPC, it is truly a multivariable controller, because you take the control moves take care or take into account all the interactions that can occur or that are there in the multivariable system. It is a truly multivariable constraints, and you see when you are doing QP, you can naturally handle all types of constraints. You can incorporate the constraints of your physical system, naturally handle constraints. Okay. Problems? Tuning, there are no standard procedures. You just have to do hit and trial, whatever works is good. Okay. How do you do tuning? How do you tune a multivariable controller is more an art. There is no systematic procedure for it. Okay. Tuning is a problem. Performance degradation. Performance highly dependent on goodness of model. I will just call it goodness of model. As your process drifts, your model which was really good is no longer as good, and you will find that just like in the Smith predictor, your performance will start to degrade and your closed loop system may actually go towards instability. Okay. Robustness is an issue. So, this is actually called robustness. Even if the process drifts, will your controller give reasonable control performance? That is the question. And of course, it is expensive. These are some of the problems. So, like I said before, since it is a multivariable, truly multivariable controller, in multivariable applications in particular, tightness of control will be really good compared to decentralized PI type of controllers. You can naturally handle all types of constraints. Like I said before, these advantages, the economic benefit that tight control and handling of constraints bring in, these must far outweigh the effort that will take to tune the controller, etc., and then and only then is it justified to apply MPC. As a short corollary, or not corollary, just as a note on history. Alright, so what I was saying was, just as a note of history or on about the history of MPC, DMC was actually formulated originally by Cutler and Ramakar, if I am not wrong. Okay. And these were not academicians, they were actually working with Shell in one of the refineries in Shell, and this happened in the late 70s. So, what I would like to point out is that this technique, the whole technique of model predictive control has its origins in the process industry and not in academics, mathematicians and control academicians and so on and so forth. Of course, once it was proposed, academicians took to it like bees take to honey and a lot of theory has come into being because of academic interest. The point is that this is essentially a technique that came out of the industry. Okay. And so, we should not think that industry nothing happens, we just operate and produce. Lots of good things happen in industry also, lots of powerful research happens in industry also. This is an example of that. Okay. I can give you many more examples, but to controls this is relevant. I think I am done. However, because we have got some time, let me just summarize what we have done over the past 6, 7, 8 lectures. We have looked at PID controllers, we have looked at how to tune them, we have looked at decentralized control for multivariable systems, and in order to understand how to tune it, we went through closed loop maximum log modulus tuning, log modulus tuning. In order to understand how the hell this came about, we went through Nyquist theorem, right half plane poles, zeros, and so on and so forth. Nyquist theorem. Okay. We also discussed in that process gain margin, phase margin. For multivariable systems, we also discussed interaction matrix, not matrix but metrics, interaction metrics. And these were Netherlinsky index, relative gain array. Okay. We also looked at decoupling, dynamic decoupling. And finally, we looked at Smith model based control techniques, model based, forgive my handwriting, and then we looked at a Smith predictor for processes with difficult open loop dynamics, and we have just finished looking at dynamic matrix control, which is actually one of the techniques for MPC. The techniques differ, the approach is the same, it is just the algorithmic details that are different from one approach to the next to the other. All this we have looked at. Maybe I should, in this context, I should also point out, when you are looking at interaction, let us say you have got a multivariable system. That multivariable system will have y output is equal to gain matrix times input, right. Well, just to, whenever you see a matrix, that is one of the things that I recommend to all, regardless of your application, whether it is a control application. In control, what you are trying to do is, given y set point, what should I do to you? So, what you are actually trying to do is, what should you be so that y is wherever I want it to be? What should I do to the input? That is the problem that I am trying to solve through that feedback loop, all right. Because you are trying to invert your open loop model, this is your open loop model, right. If I make a change in u, through the gain matrix, I get whatever is the change in y in output. The inverse problem is, I have my y's someplace, I want them to go to 0, what should I do to you? Okay. So, in controls you are always trying to invert the process model. That is just by way of, this is just a very straightforward way of looking at. Since you are trying to invert, one of the first things that you need to do is look at the condition number of k. Okay. What do we mean by condition number of k? Well, to explain it, let me tell you, well, let us see, this goes into eigenvectors and eigendirections and eigenvalues. So, to simplify it, let us just take the singular value decomposition of k. There is always a singular value decomposition of any matrix, whether it is non-square, square, fat, skinny, does not really matter. For the time being, let us just consider it to be a square matrix, because k inverse will exist only for square matrices. There is always what is called a singular value decomposition, and in singular value decomposition what you get is u and v, columns of u span which space, output space, column space of k, columns of v span of v matrix, span row space of k. This matrix is a diagonal matrix, and since it is a diagonal, the property that SVD gives, this comes from singular value decomposition. SVD is that these singular values are in decreasing order. What that means is sigma 1 is greater than sigma 2 is greater than blah 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 is greater than sigma n. Okay. Given this, also what you find is U transpose U is equal to the identity matrix. That means all the columns of U are of magnitude 1 and perpendicular to each other, orthogonal to each other. Similarly, V transpose V is equal to I. Okay. Now, when I am calculating K inverse, you see, because inverse of U is U transpose, inverse of V is V transpose. Similarly, inverse of V transpose is V. So, when I am so if K is equal to U sigma V transpose, K inverse will be U sigma V transpose inverse, and that would be V transpose inverse times sigma inverse times U inverse, and V transpose inverse is V, sigma inverse is of course sigma inverse, where the sigma inverse would be, right, if sigma is that, sigma inverse would be this times U transpose. Singular value gives me this decomposition. Notice this would be V times 1 by sigma 1 and so on, 1 by sigma n times U transpose, right. What I wanted to say was, when you are inverting the matrix, this actually shows it quite clearly. You are dividing by or multiplying by 1 by sigma 1, 1 by sigma n and so on and so forth. These are called the singular values, sigmas are called the singular values. Without going into too much theory, the point that I was trying to make was, even for if you take a decoupled system where everything is diagonal, and let us say these, for the sake of understanding, these are identity matrices, let us just say, then what you find is K inverse is this. Now, if sigma 1 is much greater than sigma n, when I am trying to invert y is equal to K inverse, U is equal to K inverse of y, that is what I am trying to do in control, right. Then what I have is y has certain deviations, I want to bring it back to 0. What should I do to U? So, therefore, I am trying to solve this equation, and when I am trying to solve this equation, if this singular value, if the smallest singular value, which is sigma n, is very small, this number would be very large, right, and if this number is very large, some of the U's may actually blow up, right. So, the point that I was trying to make, this is the condition number is defined as condition number, or let us just call it condition number of matrix K is equal to largest singular value divided by smallest singular value. Okay. Now, if this number, condition number, is large, that implies there are large singular values and then there are some very small singular values, and then when I am trying to invert the matrix, what that would cause is some of the U's will turn out to be very large numbers. So, my output has deviated only a little bit. In order to bring it back, I will have to change some of my inputs by very large amounts. Such a system is called an ill-conditioned system. Beware of such ill-conditioned systems, because it would be hard to control such ill-conditioned systems. So, when we are looking at interaction matrix and relative gain array and this and that, I think I forgot this. So, what you should do, the first thing that you should do is look at the gain matrix, calculate its condition number. If this condition number is large, beware, it is very likely that your controller will not be able to perform too well, and the problem is inherent in the system itself is ill conditioned. Maybe you are better off not controlling some of the things that you are trying to control.